All right. Thank you so much for coming. So I think we have our distinguished student here today. So today we'll talk about, remember last time we spoke about how IoT cannot work with the regular protocols. So we spoke about IP6, right? But IP6 is too big, so sluggish, and these devices are very limited in resources. All right, so we have to use 6 low PAN. 6 is for IP6, but used for low wireless personal area network. Okay, for weak devices. All right, and in the next class we're going to talk about a routing protocol, Ripple. All right, and then we're going to talk about COAP instead of HTML, instead of HTTP. Okay. All right. So these are protocols are developed to be used with IoT devices. Why? Because they are limited in abilities and what they can do. So we'll talk today. Last time we spoke about IP6. To understand the 6 low PAN protocol, all right, you have to understand IP6 because there is IP word in here missing. We're talking about IP6 again, but it's designed for these devices. So 6 low 6 low PAN is an open standard defined by IEFT. Okay, it's used for low power devices with limited processing capabilities, like IoT device. Remember, some IoT device, it's very small sensor and the small microprocessor that you need to use. All right. So it defines how it works. It defines encapsulation and header compression mechanism. So remember we studied about the header of IP6 last time. It was big, 40 bytes, and then on top of that you have the TCP header or UDP header. Now we'll try to compress it. So when there is a redundant information, we try to remove it. This way the packet will be very small. So we're going to use header compression mechanisms, which is standardized for this protocol. All right, so what are applications area? Okay, wireless internet connectivity at low data rate. That's what our IoT device is all about. They are wireless connectivity at low rates. So that's why IEEE came with 802.15.4, and it's for low power wireless network. It's used for in the 2.4 gigahertz, and also after that we had different devices that could go in different bands. An example in automation and entertainment home offices is examples for these devices, like the meters, for electrical meter and water meter and all of that. And these are part of the smart grid. So we're trying to create a mesh network. We're trying to create a mesh network, as we will see in a second. So this is an example for the network. So basically this is the internet. So internet is a collection of networks, and networks connected through routers to the internet. This is our goal in here. This is what? A mesh network for low devices. The only thing that we have, we're going to have 6 low PAN edge router, and inside either we're going to have routers or hosts. All right, routers and hosts. So the edge router acts like a router. So if this device would like to contact this device, it has to go through the edge router. Then it's part of the internet. It could communicate with any device anywhere in the internet. So where is our protocol working here? Working these low quality devices. They have low memory, low processing power, low power capabilities. Okay, so they work with this edge router. All right. So where is it running? The protocol we're talking about will be running in here and in here. So what we have edge router, we have router, and we have hosts. All right. So let's take a look at the network architecture, which we already took. So the uplink to the internet is handled by access point, okay, in the regular internet. So like in the regular internet now, there's access point. When we need to hook up to the internet, we go through the access port, right? Access point, right? All right. For for IoT, we're gonna have edge router instead, okay, which we have seen it in here, the edge router. All right. So the edge router handles the three actions. What are the three actions? The data exchange between the devices and the internet. So device would like to communicate with the internet anywhere, right? Number two, local data exchange between devices. If this device would like to communicate with device, it will be handled. And then the generation and maintenance of the radio subnet. Radio subnet that will handle the communication. Remember that we are communicating wirelessly, all right? So by communicating natively with IP, the 6LoW networks are connected to other networks simply with IP routers, as we have seen, all right? So it could be connected to any network. It could be Wi-Fi, 3G. As long as you have the edge router, you'll be able to connect it, right? So the edge router for word datagrams at the network layer, they do not maintain any application layer state. That means they are independent of the application used, okay? Stateful doesn't mean state memory. You try to memorize what application does not need to have that. So it's completely independent from the application layer. So the IP-based border routers, like the edge router, remain agnostic to the application protocol. Agnostic means they don't care what kind of applications used there. All right? Data comes from top, regardless what application, does not make difference. So the lower this lowers the burden put on the edge router in terms of processing power. So this edge router doesn't have to care about the data. You don't have to worry about that. You don't have to have further processing for the data for that sake. All right. So the IP architecture does not preclude the use of course, like proxies and all of that still needs to be used. All right. Two other devices types included. So we spoke about the edge router. What the other router and the other devices? Router, okay, which can route data to another node in the network. Call it router. And the other one is host. The other one is host that only can receive data. It's kind of a leaf. All right. All right. So what is the difference between a host? Host receives data. It does not maintain a routing table. But routers maintaining a router table. That's how router works, maintaining a router table. So host can also be sleeping device. And that's the whole idea. We need to maintain the power, the energy in the device. So these devices are programmed to sleep for a certain time and wake up for certain times to communicate, to save power. Our goal to keep their energy, their battery for a long time. Okay, for extended period of time as much as we can. So we have the sleep, awake issue as we have in most of the wireless devices. All right. So let's take a look at the stack overview. A complex application layer gateway was needed to make devices such as Zigbee, Bluetooth to connect to the internet. For these devices, we needed to have certain application layer. So Bluetooth, it needs an application layer, all right? And 6LoW, we don't have to have that. Why? Because we have it has something called adaptation layer between the IP stack, between the IP layer. Remember in the OSI reference model, we start with the physical, data link, network, transport, up to the application, right? So it will create an adaptation layer between the IP stack link and the network layer, okay? And that will enable the transmission of the datagrams through these devices, through this network, okay? All communications systems use set of rules and standards format, data and control exchange. Usually when you talk about communication, there is two kinds of information communicated, real data and control data. Control data, right? To control the communication and the exchange of the data and all of that. So the OSI model, a Wi-Fi stack example, and so In the normal OSI model, as I told you, there is a physical, and there is a data link layer, network layer, transport layer, application layer. That's the standard. In Wi-Fi stack example, you have Wi-Fi, which spans, the Wi-Fi layer spans both physical and data link layer. Then on top of that, we have the internet protocol, on top of that TCP or UDP, and then on top of that, the application, which is usually HTTP, right? Or mostly HTTP. Now, that's what we have in the 6 law. So we have the physical layer, which is the 802.15.4. This is the technology for these devices. In the MAC layer is also part of the protocol. Then after that, we have the 6 law band. That's a location. So it's kind of adaptation layer. Then on top of that, what we're going to have, the IP. So we used to have only IP. Now what we have the IP and we have the 6 law band. Okay? So it's kind of adaptation layer. Adaptation layer compresses the IP. So when the IP packets to here, it's going to come in here, it will be compressed. When it transmitted over the network, it will be much smaller. Okay? Who does that? This layer. It does compression and fragmentation. When you have a big data packet, you fragment it, and for the headers, instead of using the big headers, you compress them. Okay? So it's kind of adaptation layer. And we're gonna talk next class about Ripple, which is a routing protocol, which is more efficient than OSPF. And then in here we could use UDP, TCP, and on top of that, okay, we have the application. This could be HTTP. We don't like HTTP because it's big. We use SCOPE. We're gonna talk about it or not, or other smaller kind of applications that generate very little data. Let me go with you to the first lecture. We said IoT is about data, generating data, collecting data, sending data. All right. Unfortunately, these small devices they cannot work like this PC, function like this PC. So the data we generate and transmit, it has to be very low. And this computer is connected to a power. These devices connected to a battery. So the more data you send, the shorter the life is. The more you consume of the power. So that's why we try what we're trying to do in top of the application. We use applications that generate little data. Little data means smaller headers. Okay, when you send an HTTP packet, it has a header. When you send a COP, it has a header. So this is much more header than this. That means the data is much shorter. When it goes in here, TCP generates a bigger header than UDP. So what should we use? UDP, okay? Or for security, instead of using TLS, we use DTLS. In here, instead of using IP6, okay, we use adaptation layer, which is 6 law that reduce it. So that's the whole idea. The whole idea how to make the data smaller and smaller and smaller, yet, okay, useful and reachable, can reach to the destination. That's the whole idea. All right. So this design came out of the need. If IoT is all about big devices, we don't need all of this. Came out of the need. So when you look at the physical, let's take a look at the layers here. Physical. The physical layer converts data bits into signals that are transmitted and received over the air. Okay. So it will implement it for physical layer. It's going to use the IEEE 802.15.4. All right. Characteristics of that. Right. Then in the data link layer it creates a reliable link. Okay, where it have an error control, flow control, and all of that. All right. Part of the data link layer is the media access layer. Media MAC mixes aggregator, like for example, use collision avoidance. Okay, multiple access collision avoidance, which we studied in DCC and we studied in wireless communication. Right. So in 6 law, the MAC layer is IEEE 802.15.4. 15.4. All right. It has a standard. Okay. So that's the link layer. At the network layer, where's the network layer? Here, at the network layer. Now, at the network layer, what we have at the network layer, it will handle the routing between 2 networks, okay, and where the data gonna go over multiple hops. Hop means a router or a network, right? So IP is the networking protocol used to provide all devices with an IP address to transport packets from one device to another, from one device to another. All right? Then you have the transport layer. You have the transport layer. So the transport layer generates communication session between applications running on end devices. All right? All of us, if you're a programmer, you have worked with the TCP UDP communication. The problem with TCP is like, connection base, which is sluggish and heavy, okay? It's not good for ultra low power, devices. All right. So we might use UDP, all right, which it has lower overhead. It's a connectionless, and for security we could use DLTS to add some security mechanisms. Then at the application layer, what we said, application like HTTP, like mail, like all of these. Okay. Usually in TCP we run HTTP running over TCP. Again, HTTP is a big header, and TCP is a big header. So instead of that, we have different applications. We're going to talk about it in two classes. The COAP, Constrained Application Protocol. It's like HTTP, but has less header. It works, it's a short header. All right? So the COAP is defined by RFC and defines retransmissions, confirmable and non-confirmable messages, support for sleepy devices, block transfers, subscription support, and resource discovery. COAP is also easy to map to HTTP via proxies. So, we'll talk about COAP and all the functions that it does. Again, all of these protocols in certain layers, the function is to make a smaller data, but yet useful. So there is COAP, there is MQTT, okay, called message queue telemetry transport. So this works differently than HTTP and COAP. The way it works like publish and subscribe, okay, over TCP. So what will happen? Data is not transported directly between endpoints. And instead, a broker, which is a server, delivers a message. There is a broker, which is a server, delivers the message. So you have to subscribe for it, and you have then unpublish to it. If you need to send a message, you publish it to that broker and subscribe to it. And clients need to subscribe to it. So it introduces the topic entity, so devices can publish and subscribe to different topics. So each server is a topic, it could subscribe to that. Once the topic is updated, that a specific device has subscribed to the device will get notified and receive the data. So whenever you need to send a message, you don't send it directly to the node, you send it to entity, okay? And the entity could pull it from there. So device can use wired cards to subscribe to many topics. We call it topic in this case. So MQTT supports several layers of equality of service, QoS, making use sure that the messages are delivered. All right. So Internet Protocol version 6 over IEEE 802.15 form. All right. All right. So to recognize the increase of bandwidth of the IP6, okay. What IP6 in IP4, the minimum, this is the maximum transmission unit, okay, moved from 576 to 1280. So that's the maximum transfer unit. Remember last time we spoke about fragmentation? Sometimes we need to have fragmentation if it's bigger than that. All right. So what will happen? Ethernet is a dominant technology, and we spoke about that last time. When we say Ethernet, what is Ethernet? It's just one technology in the second layer. There is many other technologies, right? All right. So, and the throughput increased over years. So the IEEE 802.15.4 was designed to serve different market, long-life applications that require large number of low-cost, so we have a lot of nodes, but these nodes are low-cost and ultra-low power devices. Ultra-low power devices. So So the throughput under the standard is limited in the standard of this standard is limited to 250 kilobits per second. Nowadays we talk about the gigabits per second in regular real communications, right? At your home you could get 100 megabits per second. For these devices, for IoT, the standard talks about 250 kilobits per second only, which is like a quarter of a meg, all right? The frame length is only 127 bytes, 127 bytes, okay? So we have short packets or frames, and we have low speed in these devices. All right, all right. So the 802.15.4 addresses also use 16-bit short address. You know, each device has to have physical address. All right. So in here, for example, the Ethernet address is the physical address, which is how much? 48 bits. 48 bits, right? The Ethernet 48 bits. All right. The devices, it should be converted to 64 in IP6. All right. So there is two kind of 16 bits and 64 bits. Both can be used. So the EU standard interface 64 bits or the 16 bits. So it operates mostly commonly over multiple hosts. Okay, forming a low power mesh network. Right. So these devices, they have a lot of constraints. So as we say, it has about 16 kilobit RAM, 16 kilobit. Nowadays, this computer 16 meg. So it's like 1/1000 of what we have nowadays, right? And it's a very long. And the memory, the ROM, is like a chip, like a hard disk drive saves the operating system, is only 128 gigs. So it's small devices that they used for certain application. All right. All right. IP version 6 datagrams are not a natural fit for 802.15.4. Why? Because it's a very big frames, big and all of that, right? And for that, for this start, we said the maximum size of the frame is 127 bytes, and the speed is 250 kilobits per second. So we have to fix it. All right, we have to fix it. But the problem what we call it IoT. What's IoT? Internet of Things. So that anything connected to the internet has to have what? IP address. It has to use IP protocol. But IP protocol 6 is so big, so sluggish, so and these are small devices. So either we give up or we fix it. All right, and that's why we come with this protocol. Clear? Very simple, right? Okay, so the low throughput, it has a low throughput, limited buffering, and datagrams that are 1/10 of IP6 minimum MTU, make header compression and data fragmentation a necessity. So what we do, how we solve the problem? Data fragmentation and header compression. Header compression. That's it. That's what we do in this program. Okay, we compress the header and we fragment the data. All right, that's what we do. So, for example, in this protocol, okay, the headers can be limited, can limit the effective possible payload to 81 bytes. Okay, so the frame is 127. The data will be 81 bytes. The rest will be how much? 81 to 127. 40 almost.
47.
Okay, so it will be for the data. Yeah, for the data. This makes IP6 40. The IP6 has 40 bytes in the header. TCP has 20. UDP has 88 bytes in the header. Okay, it seems like it's too much. All right, it seems too much. All right. So since both low power and low throughput, in addition to RF as media, it is more prone to interference. So link failure always is much more possible with these devices. Okay, it's so thus the IEEE 802.15.4, it provides low power and low throughput. All right. So, all right. So what we have done is an adaptation. So let me go back for those who came late, just summarize what I said in a second. Okay, that's a summary. In the OSI reference model, as you know, there's a physical layer, data link layer, network layer, then a transport, right? This is what we have. In Wi-Fi, for example, we have the Wi-Fi, the IP, the TCP, the HTTP, right? So what's the problem? What's the problem now? What's the problem we have with these devices, IoT devices? They are low in processing, so they have weak processor, they have weak memory, they have weak ROM to save the operating system, and they are battery driven, right? So we have to consume, we have to have a very light in all of that. So for example, the more data you transfer, the more you consume. Each extra bit you transfer, you make the life of the battery shorter, right? So IP6 is a sluggish. Okay, TCP is a sluggish. Not sluggish, it's like big. It has a big header. IP6 has big header. A UDP has a big header still, all right? So what you do, HTTP has a big header, all right? So what is the problem? What's the other problem? The other problem, we are talking about IoT. What is IoT? Internet of Things. That means devices, these weak devices, are connected to where? To the internet. To be able to connect the internet, what you have to run? IP protocol, right? And what kind of IP protocol we're running for all this massive number of nodes? IP6. IP6 is a very huge. So either we give up, we don't connect these devices to the internet, find a separate network, or find an adaptation layer. Find an adaptation layer. So in here, for example, in the physical layer, we have Ethernet, right? We have Ethernet, or the data link, we have the Ethernet, right? In here, we have the IEEE 802.15.4. We have the MAC on top of it. Between the link layer and the IP protocol, we created 6LoWPAN, the adaptation layer. The adaptation layer. All right? So what we do generally, we're going to talk about it more, that we try to develop different protocols for communications in every layer. The goal of these protocols have to be lightweight. So as an example, you could use in the application layer HTTP, right? Using HTTP in this or HTTPS in this computer, there's no problem. There's a lot of power. There's a lot of RAM. There is a lot of connectivity. There's no problem, right? Okay. But for that, but for such small devices, it's too big. So we created another protocols like COAP, MOT, which we're going to talk about next time. That's in the application layer. When you go to the transport layer, there is two famous protocols, right? TCP, which is connection oriented, which is a big, and there is UDP. So mostly, which one we're gonna use? TCP or UDP?
TCP.
You're gonna use TCP, the big, the sluggish one?
I'll use 6LoWPAN.
Huh?
No.
Which one are you gonna use?
UDP then.
What's the difference between TCP and UDP?
Connection.
Okay. What other difference?
Lightweight.
Lightweight and heavyweight. So which one are you gonna use for IoT devices? The lightweight. Which one? UDP. All right. Now for security there is TLS, which is the standard, which is also sluggish. What we don't use it. What we use DTLS because it's like a compressed version. Clear? All right. When you come down in here, you must have an IP address because you are connected to the internet. Internet without IP address does not work, right? All right. So what we do, we created an adaptation layer called 6LoWPAN. What does it do? Compress the header. So the header has a lot of repeated information. Compress it. And fragment the data. All right. That's the adaptation layer. All right. For network in the routers level, we use OSPF, okay, different protocol. And here we came up with the Ripple, something called Ripple. We're going to explain it next class, is as a routing protocol. Right? All right. All right, so that's what it is, okay? So that's what we are trying to do. So today we are focusing in this one. Okay, what does this do? One, compress the IP packet and fragment it to make this more data. Okay, that's what we were talking about this so far. All right, I'll continue.
Professor,
Yes,
we designed IPv6 because there weren't enough IP
IPs,
addresses.
yes.
So will the compression still maintain that uniqueness?
Sure.
Even,
That's-
okay.
Yes,
Even after compressing, we'll still have unique.
absolutely. Okay, and the reason for that, okay, let me tell you, I'll go back in here also. So this is how the network. So this is the whole internet, right? So you have a router. What is internet? It's a collection of routers. And each router connects to a network, LAN or WAN, right? Okay. Now for IoT, we have a mesh network. All right. The interface is not router anymore. It's a router that's running 6 low band edge router. We call it edge router. Edge router, right? And inside the network, we're gonna have routers and hosts. What's the difference between a host and a router? Router always has the routing table. Host does not have routing table. All right. So now, when they communicate locally in here, we don't need to have the prefix because they are part of. Remember, the IP address is 2 parts: prefix and host. Right. Right. Remember the the IP address usually. Okay, host and the prefix, right? What is the prefix in here? The network address. Do you agree? And this is the host, right? All right. So all of these in here, they are from the same prefix, the same network. So do you need to send the whole IP address? No. You need to send the host. So what you did here, compression for the IP address. What is the size of the IP address? 128-bit total. Source and destination, 128-bit. So you could, in the communication within the network, to compress the IP address. When you compress the IP address, what we did? Reduce the data, reduce the header. That's the whole goal. All right? So that is still you are using the IP address. All right? We're going to see how compression is done. All right? So that's the whole idea, right?
Professor,
Yeah.
like without the prefix, how it's going to figure out what is the gateway of?
It does not need to have a gateway because what I'm saying in here, this leaf communicating with this leaf. All of them, they will have the same prefix.
So we don't want in this network.
We don't want?
We don't want within the mesh.
Yeah, within which we don't need it. We don't need it, right? So let's say that you live in a street called Atlantic Street. All right? In Atlantic Street, what do you have? Houses. Each house has a number. Okay? Okay, odd and even. Right? Odd and even. Let's say this street, you are all family. All the houses are the same family. Okay? So when you need to send, for example, you cook, and you need to send one dish to your cousin. So you tell your son or your brother, get this dish to house number 58. Do you need to say Atlantic Street? Okay? Because you are living all in the same street, right? And you communicate. Do you say you have to say 58 Atlantic? It's only Atlantic Street. It's not Atlantic. Same thing. All of these hosts have the same prefix. Do I have to include the prefix in all of that? Okay? I'll give you an example. You're sending a mail in the United States. How many times you write USA? You say I'm sending a letter to 221 University Avenue, Bridgeport, Connecticut 06604. How many times you write USA? You don't write USA because it's this a prefix. It's known this is going to. But if you are sending internationally, you're gonna write the country. The same thing in here. So you compress the address. All right, to a certain level that makes the address still meaningful. Okay. Now your question: if this one would like to communicate with this one, does it need to include the prefix? No. Why? Because this one cannot send directly to this. It has to go to where? To the router edge. The router edge can put the full address and send it out. Right? So we compress, and not only the address, we compress many things. I'll show you some examples. Where did I stop? So we'll come to header compression in here. So it compresses the 40 byte of IP6. So if you go to the previous class when we studied IP6, what is the size of the header? 40 bytes. All right. And for UDP, what's the size of the header? 8 bytes. Okay. By assuming the usage of common fields. So there is a common field between these headers. Remove the common things. Remove them. Don't have to repeat them. All right. Header fields are elided when they can be derived from the link layer. There is some information can be derived from the link layer. What is link layer? It's the second layer. You're gonna go down, right? Okay, you remove it. If you can know it at the link layer, remove it. Okay. Standard only supports IP6, not IP4. IP6. Okay, compress all headers, the adaptation, the network, the transport layer. All the headers will be compressed down to few bytes. All right? There is a way to compress it, right? There is a mechanism. 1, 2, 3, 4. Compress it. All right. Without losing necessary information, without losing information that we need for the packet to be delivered. All right. We're compressing it. So the SIT-low adaptation layer also removes duplicated information that can be derived from other layers, such as the IP6 addresses and UDP length fields. You have the UDP length fields. Okay, part of the header for UDP is the length. Do you need it? You don't need it because you could derive it, you could calculate it from when it goes down to the IP layer. So don't include it, right? So for example, if you remember from last class, this is the IP6 header. We spoke about the version, traffic class, flow label, payload length, next header. Remember, we could have multiple next headers, right? And hop limit, source address, and destination address. This is 40 byte. What we call this, the base header. You always could have extension headers, right? That's what we explained last time, right? So look at the 3 levels of, so in here, for example, you could compress it to 2 bytes. So from 40 bytes to 2 bytes. Or you could compress it to 12 bytes, 40 to 12, or from 40 to 20 bytes. So it depends on the location. This will explain it. So it's a stateless compression used, which does not require any state and lets routing protocols dynamically choose routes without affecting compression ratio. So, in the first case in here, where we compress to 2 bytes, what happened? Communication between 2 devices inside the same network using link local address. We are using link local address. All right. So the IP6 header can be compressed to. So we compress it to just the link header address. Okay, we come to link header address. Okay. In the second one, communication distant to a device outside the network. So we're going out of that circle to outside. Okay. Then it could compress to a 12 and for a 20. All right, so there is a mechanism for that. I mean, I'm not explaining the mechanism here, but you could know it. You go to the RFC and you could learn. But the idea here of this protocol is to compress what? The header. When you compress the header, that means you have less data transmitted for every frame. That means you preserve power, more, you reduce the amount of data is communicated, right? Then the other thing, the fragmentation. When you have a big data, you could fragment it. And we spoke about fragmentation in a simpler right time. So the data link, okay, with a frame length of a maximum 127. So the standard, okay, for this is 127 bytes, okay? But that's way less than the MTU of the IP6. So IP6 could be a big packet. So I could chunk it, I could divide it. It should not, so the maximum, again, the maximum size of the IoT device, okay, it should be 127 byte, but the MTU for IP6 it could be 1,280. You could receive a packet that size. So in that case, you have to divide it to how much? You have to divide it to how many packets? 1,280 divided by 127. Okay. Okay. 80. Okay, will be divided to, okay, it will be divided, right? All right, so that's the fragmentation. So it should be noted that frame format, okay, in G does not have the same limitation. Anyways, we are talking not in the G, we're talking about the 802.15.4. In order to enable the transmission of IP6 frames over IEEE 802.15.4, okay, radio links, the IP6 frame need to be divided into several small segments. For this purpose, additional data in the headers are generated to reassemble. When you do fragmentation, you have to add some information in the header for the destination to know how to reassemble it together. Okay? It's exactly like when you buy, for example, a motorcycle. If you buy a motorcycle, right? How you buy it? By mail, they ship it to you, maybe they ship it parts for you. And you have to build it together. So if you put the boxes coming for the motorcycle, it's bigger than a motorcycle by itself. Why? Because they fragmented for you and you have to reassemble it. So reassembly, you know, you put it in the boxes, they put instructions for you and all of that. I understand the idea. So when you need fragmentation, that's good. The idea of doing fragmentation is to make the packet smaller. But to be able to reassemble, to join, to paste, again, that you have to have extra data to tell you how to do it. And that's what is happening here, right? That's what we are talking about. All right? So for this purpose, additional data in the headers are generated to reassemble the packets. And we spoke about fragmentation and reassembly also in IP6 last week. All right. So when data packets are reassembled, the additional information will be removed. You don't need them anymore. So fragment and then reassemble them, and the additional information will be removed. Okay, I will go back to the motorcycle. They send you tools, right? So once you assemble the motorcycle, do you need the tools? You don't need them, right? You throw them, right? Or whatever, or the foam, or the protection, or all of that, right? All right. So in the case of there is two kinds of networks. There is something called mesh under, and there is something called router over. Mesh under and router over means over the router or in the mesh. So let me show you the figure in here. So there's two ways of communication, the routing. So the data will go from application, transport, network, data link, physical. This is the router. It's gonna go all the way to where? To the router, to the network layer, and down again to the network layer, the other router, until it goes to the destination. That's what we call it, router over. Router over. It goes through the router. Okay, this is for the normal communication. That's for any node in the internet connected this way, right? So it has to go through the network layer and at each router, right? Because we put all the IoT devices in a mesh network, we could avoid going through the routers and communicate through the data link, only through the data link. So the data does not go all the way to the network layer. Right? It does not go all the way to the network layer. Right? Alright, so there's two ways of operation, as we said in here. Okay, so there's mesh under and network over. Okay. Alright, so stateless auto configuration. Okay, so one advantage, we spoke about that also in IP6, that the nodes can configure their IP addresses, right? Automatically. So they take the physical address, 64-bit, put it at the beginning, and then they could get the prefix and automatically figure out their IP address. So you don't have to assign an IP address. It will be automatically. What is the problem with that? Sometimes you could have duplicate IP address, which bad, but that's a problem was solved in IP6 by having a protocol called DAD, which is duplicate address detection. All right, so that will be nice to have auto configuration for the IoT devices because they are in millions. If you're building a wireless sensor network that has like 1,000 sensors, do you think you'll have time to go for each sensor and assign IP address? No. I mean, you have to have a auto configuration. So each node will get its IP address, okay, from the pool automatically. You don't have to worry about that. One thing you have to worry about it, you cannot have duplicate IP address. You cannot have a duplicate IP address. But again, you don't have to worry much about it. Why? Because we have a protocol called duplicate DAT, which is part of IP. So these are the header frames. So the header, of course, you have the IP payload coming from application, right? Goes to IP. Then you have the IP header compression. Then it goes to the link layer. Or it could IP, then the header compression, or the fragmentation header. If the packet is too big, you have to fragment it. So it will add a header for the fragmentation. That's what we're talking about. We're going to add more data to be able to reassemble, and then the link. Okay? You could have the IP payload, then the header compression, the fragmentation, then the mesh addressing header when the devices are in the same mesh network. Okay? Clear? All right. So the header format, okay, 3 subheaders are defined: mesh addressing, fragmentation. I will explain that. Okay, I will explain that. Okay, let's talk a little bit about routing. The data will be routed. So what is routing? Is how to move the data from one network to another network, right? That's routing, right? Routing involves a router. Routing involves router. Right? So usually the not this one is yeah. So this is a router. So you have a source, you have a router, until it goes to the destination. So the data will go from the application to the physical, go through the router up to the network, and then goes down up to the network, and goes down up to the network until it gets to the destination, right? All right. So that's what is routing, until it gets to the destination. Router has how many layers? 5? 3. It has the physical layer, the data link layer, and the network layer only. Okay. A host has how many layers? 7, supposedly, right? 7. So, okay. So when you talk about routing, okay, 2 categories of routing. There is a mesh under and router over, which we explained it. Okay. The mesh under is the simplest. It's kind of a local network, kind of a LAN, all right. So it does not go up to that. So routing of data happens transparently. Hence, mesh under networks are considered to be one IP subnet. It's considered to be one IP subnet. The only IP router in such system is the edge router. So the only router in such network is the edge router. So one router. All right. So one broadcast domain is established to ensure compatibility with the higher level IP. Okay. And the message have to be sent to all devices in the network, resulting in a high network load. Mesh under networks are best suited for small and local networks. So you build a small network, make it work like a mesh network, mesh under. Okay, mesh under. Ready here? Okay, you make it as mesh under, right? If you need to make it look like any other node in the internet, we're gonna use what? Route over. We're gonna use route over. So the routing takes place at the IP level. which is the third layer, all right? Okay, so most widely used routing protocol for routing, okay, Ripple is the most important protocol. Ripple we're gonna talk about in details in the next class. Maybe we'll talk a little bit about it now, all right? So from your background in DCC and other classes, what is router? Router is a we call it multi-host device that has two interfaces, right? So right? So you have, for example, a LAN here, right? Which has a few PCs connected, and you have another LAN which has, for example, a star, whatever topology here, all right, connected. So if this is from certain subnet, let's say 216.87.111 XX whatever, okay, and this is 218, for example, .30.40 XX, all right. So for a node A to be able to communicate with node 1 in here, it has to go through a router. Okay? It has to go through a router. This network has to be connected with this network. Right? So router is a multi-host device. So you could make this computer a router by having two Ethernet cards. Alright? Two Ethernet cards. So if you give this, for example, this Ethernet card 1 and this Ethernet card, this 1 and 2, the interface, the physical. So if you give it, for example, from here 216.87.111.1, and you give this from this one in here, give it from here to 18.30.40.1. All right. So this node will be able to communicate with this interface. In here, it could translate the data, store and forward to this link, and this link can be this interface can communicate with the other network, right? So it's a multi-home. That's what is router. So router does not have application. Is there an application? There is no application. Okay, there is no presentation. There is no session. Okay, we have a physical layer because we have Ethernet, and we have link layer, and we have network layer. 3 layers only, right? Right? 3 layers. All right. So, so router usually connects multiple networks. It could connect multiple networks. I mean, it's not only 2 interfaces. Could have multiple interfaces. Could have 3. Could have 4, and many. Right. So when the packet comes from here to the interface 1, how it know it gonna send it to interface 4 or 2 or 3? From something called routing table. Routing table. There's something called routing table. Table. It tells you if it comes from this network, send it. If it comes from anywhere and it has to go this destination, send it to this interface. 1 or 2 or 3. Right? Routing table. Right? So how is routing table is collected? How is it built? Is it static? It could be static. But networks keep changing, right? Static for a small network. But for real life, it's not static, it's dynamic. How is this router, how this table is built? By something called routing protocol. Something called routing routing protocol. So there is many routing protocols out there. The routing protocols used for regular router like OSP, FL, okay, or RIP or different one, they are suitable for normal networks, but they are not suitable for small networks. IoT do. So that's why we came up with something called Ripple. All right, Ripple, you don't use it in normal network. You use it for the small. You understand the whole idea? Okay, so you know what's Ripple? It's a routing protocol. Okay, what is routing protocol? It's a protocol that builds the table in the routers. What is the function of the table? To be able to route the data, because the router connects many networks. What? That's what the router is for. So the most widely used routing protocol for route over network is Ripple, pronounced Ripple. Okay? All right. So it specifies the IEEE, the IP6 routing protocol for low power and lossy networks. So Ripple, it's a routing protocol for this kind of networks, low power and lossy networks, which provides mechanism whereby multi-point, two-point, you could have multi-point, two-point. All right. What do you mean by multi-point, two-point? Let's go in here.
A lot of hosts to one router.
Like what?
Like the number of hosts to a router.
To a router, like the edge router, right? Here. So this is our multi-points, all of them sending where? To the edge router. So this is multi-point to a point. The other way, what we call it? Point to a multi-point. Point to a multi-point. And the third way of communication is point to point. So we have multi-point to a point to a multi-point, and point to a point. And Ripple will take care of that, right? All right. Again, what's the function of Ripple? To building the routing tables. So how exactly the data will be routed. All right, where are we at? Okay, so which provides mechanism whereby multi-point, two-point traffic from devices inside the network towards a central control point. Okay, as well as point to multi-point. All right. All right. So that's what it is. Point to. Okay. Now there's two kinds of nodes. So Ripple supports two different routing modes. Something called storing and not storing. What does it mean storing? That means the nodes store a table. Routing table. Non-storing, the nodes does not store. So they work differently. All right. What's the advantage having it not storing? You can have a very low memory. If you need to have a storing, it has to store the tables. It will need more memory, right? All right. So a storing model, all devices in the network configured as routers maintain a routing table. All of them will have the routing table. All the nodes will have the routing table. The routing table is used to look up routers to devices, and the neighbor table used to keep track of nodes' direct neighbors. Non-storing mode is only devices with a routing table is edge router. So the only one has a routing table edge router. That means what? Any communication has to go through what? The edge router. Why? Because the edge router is the only device has the map. Right? Has to go up to the edge router and then send. All right? All right? We spoke about auto configuration. Auto configuration is we're going to talk about Ripple in detail next class, by the way. Just to give you an introduction. Okay. So auto configuration is autonomous generation of devices' IP addresses, and we spoke about that last time. That there's a mechanism that you could open the IP addresses. Also, security. The link will have. AES link layer security, okay, and you could have link authentication and encryption. You could have link authentication, and there's a difference between authentication and encryption. We spoke about it. Encryption that to keep the data private. Authentication to authenticate where is it coming from. So, for example, if tomorrow if you receive a message that there is no class next week, do we need to keep this message secret? No. But you have to make sure it's authentic. There's a difference between authenticity and secrecy, right? Also, it provides interoperability. Okay, so these are references, you could go over that. So today, basically we went over 6LoWPAN, which is an adaptation layer for IP, okay? And that's what we'll do in the next classes. We'll see the new protocols are produced, are developed to be able to adapt for IoT devices. Thank you.